Good evening, my dear lions. Welcome to the Vedantu NEET English channel. Hello, Aparna. Hello, Madhumati. Hello, Trisha. Good evening. Good evening. Uh, Uday Prakash. Yes, your captain is here. So we're starting off with the 12th standard syllabus and the first chapter of your NCERT, Electric Charges and Fields. We will try to complete as much as possible, and if it takes too much of time, then we'll probably divide it into two parts. Okay, so we'll see how the lecture goes. Welcome aboard. It's going to be around 2 to 3 hours. That's the expected timeline. And this is your captain Shreyas on the Vedantu NEET English channel, teaching and nurturing kids for more than 13 years. And this is now your opportunity, your time to get yourself thorough through all the concepts, to get yourself guided by my particular teachings and experiences, and make sure that you crack NEET exam and any other competitive exam that you're going to give the following year. Okay, so make sure you're liking the video. If you have not done that yet, give your Guru Dakshina by smashing that like button and stay subscribed so that you will not miss any other class, or else you might just lose track of where did I watch, sir? Where did I see this series? Yes. Hello, Shruti. Hello, Satyashri. Good evening, Krishna. Warrior Pandus are here. Hello, Gautam. Hello, Naina. Pratibha, welcome, Madhumati. Yes, thank you for all the lovely hearts and the lovely welcome. Let's begin with the class. Okay. Now, this is a big chapter and carries high weightage. A lot of concepts, obviously, a lot of things are there. And it's not just important from your board's point of view, but also obviously NEET point of view. And this chapter of electric charges and fields, like you can see over here, it starts by the understanding of what charges are and what forces do charges apply. And then we slowly move to the concept of electric field and electric flux. And towards the end, we deal with something called as dipoles and also Gauss law with its applications. That's what the broad outcome of this chapter is. Okay. There is a second chapter following this, which is electrical energy, electrical potentials, capacitance, and all of that. That is the chapter number 2. This is chapter 1 of 12th standard. Okay. So let's begin. Hello, Shruti. Hello, Trisha. Hello, Manoj. Good evening, my dear lovely warriors. See, the concept of charges, that's what is there in the introduction. The concept of electric forces was known much before, and people knew it by experience, and it was slowly formalized later on. Like we all have experienced some kind of a spark or heating of a crackle when we take off your clothes or sweater, particularly in dry weather. And sometimes you might have tried to rub a scale and touch bits and pieces of paper, they get attracted. When you remove your shirt, suddenly you feel some spark. Or when you touch somebody, you might have felt a shock. All these are related to electrostatic charges, the charges which are there around us. Even lightning, thunderstorms, they involve electrical charges and forces obviously in them. So you might have also heard this is due to generation of static electricity. This is the precise topic which we are going to discuss in this chapter. Static means anything that does not move. So this is a very important word over here. Static means anything which does not move or change with time. So that is why the chapter's name is sometimes referred to as electrostatics. It is also referred to as electrostatics. Okay, so here we'll be dealing with the forces, the fields, the potentials, etc. due to stationary charges only. So that is why static, electrostatics. Cool. That is the basic introduction part. Now this is where the real chapter actually begins. Now see, if something has to apply force, something has to cause some phenomena, it has to be due to something very preliminary, something very elementary, something which happens to be found in nature. And that is basically your charge. That charge which is there in all the bodies around us, in all the atoms and the molecules, that is the thing which causes, that is the thing which causes the forces, the crackling, the thunderstorms, the lightning, the sparks, the static behavior, electrical discharge. That is that thing. So historically, the credit was given to, a long time back to Greece around BC, and that's how the name came, okay, from there. Many such pairs of materials were known which on rubbing could attract light objects like straw, pith balls and bits of papers. So just imagine this. This is a lot of time back, thousands of years back. People knew that when you rub some cloth on some object, or if you rub two objects together, they were known to attract or repel few things. So people knew that there is something, and they attributed it to something called as electron, meaning amber. And there were many such pairs which were known on rubbing. They would attract, objects like, plastic, paper, or pit balls and stuff like that. So that is what, the history of charges. All right. And we all know that when you take a glass rod and you you know rub it with different cloth, and if you touch it to another plastic rod or another glass rod, either they will start repelling or attracting each other depending on the charges which are present on the other body. This is something which you have already seen as either in 9th or 10th standard, or you would have experienced this in your school when you take a plastic scale, rub it on somebody's hair, and you attract bits and pieces of paper. 100% you would have done it. Yes, Trisha, it will be around 3 hours. You can expect it. Always go with new NCERT. Yes, always go with new NCERT. Do not use the old NCERT. So this is interesting to see that when a glass rod is rubbed with silk, the rod will acquire some kind of charge, and the silk acquires some another kind of charge. And this is true for any pair of objects that are rubbed to be electrified. You rub Pandu against Champa, Pandu will become one type of charge, Champa will become other type of charge. Pandu becomes positive, Champa becomes negative. You rub Champa on Laddu, Laddu will become negative, Champa might become positive. So they become electrified. They become charged bodies when they are rubbed. So what happens is when you rub, two objects onto each other, or the charges of one kind go on to the other side. So the charges of one kind go on to the other side. So one becomes maybe positive, the other becomes negative. So it depends on the pairs of the bodies. This depends on the pairs of the bodies which are being rubbed. Okay. It's not like every time the first object which you rub only will become positive. It depends on the material. Okay. So you will see that if the electrified glass rod is brought in contact with the silk with which it was rubbed, they will no longer attract each other. They will also not attract or repel other light objects as they did not being electrified. So you will see that if you just bring them close without rubbing, they will not attract or repel. It's only after rubbing that they were getting electrified. That means that rubbing action was involved in electrification. Just by taking that glass rod near that cloth, it will not do anything. Rub it, then that electrification process happens. So why do they acquire charge is something which we'll get to know from this particular thing. All material is made of atoms, molecules. Although most of the materials are neutral, they do contain charges. Just think about it. Even in an atom, there is a positively charged nucleus. There is a positively charged nucleus, and the negative charges go around it. The negative charges will go around it. As many number of positive charges are there, exactly that many number of negative charges are there. So as such we know that the atoms are electrically neutral, but they do contain charges. They do contain some positive and the negative charges which are exactly balanced. Now what happens is that when you rub things, you will see that, okay, all these things are basics. There is nothing great over here. They are just mentioned that, there is atoms and these molecules hold these charges together, etc. Now, this electrical forces play a very important role when you rub atoms together, when you rub molecules together, when you rub objects together. That is explained in the next slide. You will, or maybe over here only. What happens is these electrons which are orbiting, they might get knocked out. They might get knocked out and move on to the other atom. They might get knocked out and move on to the other atom. So what happens? Imagine this atom loses few electrons, it will become less negative, which means more positive. These electrons will jump onto something else, that will become more negative. So that is how that electrification process happens, because these electrons jump from one to the other when you rub them. And there are certain kind of atoms which love those electrons, they will pull them. Certain atoms also love those electrons, but maybe they are not able to hold them so properly. So there is no good adhesion. Adhesion is when things stick, when things attract, things stick together, that is adhesion. So maybe that adhesion or the liking towards that electron is not that great, so it is not able to control that electron so much. But some other atom which has come close to it by rubbing action, you will see it is able to capture that electron and take it away, so it becomes more negative, this becomes more positive. Is that point clear? How this electrification process happens? Everybody? Yep. Awesome. Awesome. For more physics classes 3, you should be a part of the DNA batch. I'm taking almost 4 classes per week, 2 hours. It's crazy the amount of content that I am giving. Yeah. Yes, it can't believe, but it is true. Now, once a body gets charged, once a body basically gets charged with this, you know, you can detect whether a body is charged or more charged or less charged or not charged at all using this device called as electroscope. So what is an electroscope? Electroscope is a simple apparatus to detect a charge on the body, which uses the gold leaf as an setup. What it consists is, there is a metal rod in a box. You can see there is a metal, that orange thing is a metal rod in a box with two thin leaves attached at the bottom end. Imagine this is a rod and there are two leaves, like the plant leaves are there. Imagine two leaves in the bottom. Okay, and all of this setup is inside a box and it is filled with insulation, and there is nothing which can conduct out or inside that rod. Now what happens is, there is a small point of contact on the end of the rod at the top, which is also called as the metal knob, through which the charges can enter or exit, because everything else is insulating, nothing else can enter or exit through that rod or from anywhere except that top point. So what happens is, if I have a charged body, imagine my head is charged. So I bring my head close to that rod and I touch that rod's top knob. What will happen? The charges will conduct through that rod and they will go till the very end of the leaves. Those two leaves will become charged. The moment they become charged, they will repel. They will repel. The moment these leaves go like this, I'll be like, yes, there is a charge on my head. Then I call Champa. Hey, Champa, come here. Let's see whether there is a charge on your head. So Champa takes her head and puts her head on this knob and touches it like this. Champa puts her head on the knob. The charges through Champa flow through that rod and enter the leaves till the very end. And the leaves go even more. Then Champa is more charged. If the divergence is more, there is more charge on it. So the degree of the divergence is an indication of the amount of charge. The degree of divergence is an indication of how much charge is there. Then Laddu comes. Hey Laddu, come, bring your head. Laddu touches that particular metal knob over here. The charges, if at all, flow. And I see that the leaves are not going only. Then I'll say, Laddu, listen, there is no charge on you. The leaves did not move at all. So no charge, no divergence. More charge, more divergence. Got it? Understood? All right. Perfect. Perfect. Guys, I need more attendance, Harborine. That's all. Yeah. All right. Now, conductors and insulators. Now that we understood what a body will be charged, not charged, how to detect that charge. All right. So we have till now focused on how the charges get transferred from one body to other body, how different pairs were identified even thousands of years back. And then we also saw atoms are neutral. There is equal amount of positiveness, negativeness. And electroscope is a device used to measure how much charge is there, more or less, or no charge at all. Now, there are basically two major objects classified. as conductors conductors and insulators, depending on their electrical behavior. Conductors are the ones conduct electricity. Insulate, that means you separate out. That means they do not conduct electricity. So some substances readily allow passage of electricity through them. Some substances readily allow the passage of electricity to them. Others do not. Others do not. Others do not. Those which allow electricity to pass through them easily are basically called as conductors. They are called as conductors. And which are conductors? Basically, most likely metals, humans, and even animal bodies, and even Earth are very good conductors. They are very good conductors. Earth, human body, most of the animals. Basically, if you touch a loose wire, you will get shocked. You will die also. Even an animal, by mistake, if it happens to touch these wires, they will die because they can conduct electricity. Most of the metals, aluminum, gold, silver, copper, all these also can conduct electricity. Whereas you will see the most of the non-metals, most of the, not all, like glass, porcelain, plastic, nylon, wood, they offer very high resistance to the passage of the electricity to them. They are called as insulators. They are called insulators because they offer high resistance. Most substances fall into one of these classifications. Anything that you take around you, either it will be an insulator or it will be a conductor. Later on, you will see there are certain devices which are like conductors, like insulators, somewhere in between, they are called as semiconductors. There is a separate chapter for that. That is towards the end. That is towards the end. Okay, don't worry about it right now. So basically, the reason why certain objects are like conductors is only because they have free electrons in them. They have free electrons in them. You can see they have electrical charges, electrons, comparatively to the non-conductors or insulators. So what happens? These free electrons can easily flow. They are ready to move. They are ready to conduct. That is why they behave like a conductor. That is why they behave like a conductor. Now, we have laid the basic foundation. Now let's talk about charges. All right. So whatever charges, whatever things which create that crackling sound, thunderstorms, which attract bits and pieces of paper, when you rub glass rod on wool, they can attract some other objects. There is some kind of attractive and repulsive forces between them. Inside an atom also, there is some positive and negative charges. These charges obey certain basic rules, some basic guidelines, have some properties. What are those properties? Let's have a look. First of all, you should know that there are two kinds of charges. Whenever you talk about charges, either it can be positive or it can be basically negative. There are certain objects which do not have only any charge, and that is basically neutral objects. Neutral objects. Example, neutron. Neutron does not have positive or negative. It has no charge at all. The example of positive charge is basically a proton. Proton has a positive charge. The example of a negative charge, nothing but an electron, which has a negative charge. So what are the basic properties? There are three major properties: addition, conservation, and quantization. We'll talk about it. But remember, most of the times we treat our charges like point charges because the size of a proton, the size of an electron, the size of a neutron for our day-to-day activities is so small, you can treat it like a point. So most of the times we treat them as point charges. The size of the charges are very, very small as compared to the distances between them. Hence, we treat them like point charges. Usually, you will see, we'll show the charges like a point. Although the size of a charge might be there, but for our day-to-day activities, it is very, very small. So what are the basic properties of charge? Guys, first one, addition of charges, meaning this is completely based on the property that charges are basically scalar quantities like mass, time, right? Volume. All these are scalar quantities. So you can just add the charges. If there are two or more charges, I can say that the total net charge is just Q1 plus Q2 plus Q3, like that till Qn. I can just add them. That is the meaning of addition of charge. Now it might happen one of the charges plus 2, another charge is -3, another charge is plus 4, another charge is -7. You have to do algebraic sum only. So 2 minus 3 minus 1 minus 1 plus 4 plus 3 minus 7 is -4. So you know the total charge will be negative. So that way you have to consider the signs also while adding. Just don't take the magnitudes, which is common sense. The total charge is basically conserved. This also kind of makes sense. The total charge is conserved because no matter what happens, you cannot destroy that charge, or even if it omit a charge. Just imagine, say for example, there is a neutral body, no charge is there. You destroyed somehow, you will see an equal amount of positive and equal amount of negative will come. So earlier charge was 0. So you'll get +2 positive, +2 negative. Still the net charge will be 0. Same way, no matter what you do, let's say you rub body and you see one body becomes positively charged, like, sir, this become positively charged, sir. So how is charge conserved? Remember, the other body has got negatively charged. The other body has got negatively charged. So the total charge in this universe will remain conserved. So the total charge initially, the sum, is equal to the total charge finally in this universe, or basically in an isolated system. In an isolated system. So if we take an isolated system, you'll see whatever was there before will be there afterwards. Best examples like this. Imagine one is +2, another is -5. This is there before. Let's say this object becomes, -1 charge. So how much charge will be there on the other one? Just calculate the total. Just calculate the total. 2 minus 5 is basically -3. So the total should still be -3, which means the charge on this object will be -2, because -1 -2 will become -3. So the net charge remains conserved for an isolated system. Yep. Is that clear? Very, very important. Isolated means, like, imagine you're inside a classroom and teacher locks the door. Isolated. Nobody will go out, nobody will come in. That's it. That's an isolated system. So no charge can go out, no charge can come in. Last one, quantization of charge. We'll talk about it, I think, in the slide after this. Yes, quantization of charge, which says that every charge is a integral multiple of some basic charge, and that basic charge is the smallest charge possible. You cannot go beyond it. Just imagine, for example, I tell you, hey, in this world, Shreyas Sir says, you can only have 200 rupee notes. You can only have 200 rupee notes. So a person can have 400 rupees because he can have two 200 rupee notes, can have 1000 rupees, can have basically 5 200 rupee notes. But can a person have 150 rupees? No. 250? No. 377? No. 1688? No. 1600? Yes. Basically, all multiples of 200 are allowed. That's the smallest denomination allowed. This is the quanta. This is the quanta of money, and you can have only 200 rupee notes in this new world. So same way, it is found that in our universe, the smallest charge which God gave us is 1.6 into 10 to the power -19 coulombs. Coulomb is the unit of charge, which is also the charge of an electron or a proton. You can't get a charge lower than that. Any charge around you will be a multiple of this. Will be a multiple of this. That's what it means. So you will see any charge is n times of E. Thus, the charge Q on a body is a multiple of E. That E is the basic unit of charge, and n is basically any integer, which could be positive or negative. This is also, this basic unit of charge, like I said, is also a charge on an electron or a proton. By convention, the charge on an electron is taken to be negative, Therefore, the charge on an electron is written as negative E, and that on a proton is positive, which kind of makes sense. Okay, so the charge on a electron is negative E, whereas the charge on a proton is positive E. Because proton is positive, this is just convention. You can ask, sir, why electron is taken negative? Sir, I feel bad for electron. Why not electron is positive? Fine, you take electron as positive, then proton will be negative. Then the whole history will change. Then each person will come up with their own reason and convention. So we need as a standard. So take an electron as negative, proton as positive. Let's not debate about that. This principle, because electric charge is always multiple of a basic charge, this is called as quantization of charge. When it is an integral multiple, that is called as quantization of charge. Now, usually what happens is the number of charges which you are dealing with. Let's say there is a lump of stone, it is charged, or my hand got some static, or there is a car which is moving, the metallic body got some charge on it. There is a thunder, lightning happening, there is some charge in it. Okay, or some electrical circuit is there, some charges are there in it. So in usual day-to-day activities, the charge that you deal with, although it is not very large, it is small only, because if it is too large, then it will give you a big shock. And uh, even if you are taking a decent amount of charge, there are so many electrons or protons in it, there are so many electrons and protons in it, that you virtually don't see much of difference in this quantization principle. Just imagine if I talk Ambani's wealth. Ambani's wealth, okay, has he has, sir, something, some crazy amounts, sir, to this something 5 6 7 6 8 0 0, something like that. You will not think whether it is an integral multiple of 200 rupees or not. You will be like, okay, fine. Even if there is something wrong, let's say by mistake, I wrote, 827. I know this will not be an integral multiple of my basic 200 rupee note, but I will be like, okay, fine. Even if it is supposed to be 800, that 27 rupees will not make so much of a difference to his wealth. Getting my point? So when we deal with too many electrons, okay, it's okay to not worry about this principle so much, because a small difference here and there in writing the value in the last decimal will not change our result or calculation so much. Is that okay? Everyone with me? So uh, that is something which you should know. And here they have just talked about who discovered it and who demonstrated it. So maybe in match the following you might get it sometimes. So just for that, so the quantization of charge was first suggested was suggested by the experimental laws of electrolysis discovered by Faraday. Michael Faraday suggested this, but it was experimentally demonstrated by Millikan in 1912. So it was suggested by Faraday, but it was proven by Millikan. Millikan oil drop experiment. Cool? Everyone with me? Yes. E is negative, and for proton it is plus E. Yes. So we are going to take the magnitude most of the times. So what's the value of E? That is also given right over here. Like you can see, E is nothing but 1.6 into 10 to the power minus 19 Coulomb. So if you are wondering how Coulomb is defined, it is defined as the amount of charge which flows when you take 1 ampere of current for 1 second. That definition has been mentioned here. So the SI unit of a charge is basically called Coulomb and is denoted by the symbol C. In terms of the current, it is defined. So 1 Coulomb is the charge flowing through a wire in 1 second for a current of 1 ampere. Current is a fundamental quantity, charge is a derived quantity. Please remember, charge is basically a derived physical quantity. Derived physical quantity. Keep this in mind. Okay, everyone, till this point. Now, if you notice the amount of charge of a proton or an electron, it is so small. 10 to the power minus 19 means so many decimal places you have to go to get one non-zero number. So it is very, very small. So if you take 1 Coulomb charge, imagine the number of protons or electrons in it. Positive 1 Coulomb or negative 1 Coulomb, there will be around 10 to the power 18 electrons. Now 10 to the power 18, when you write it is okay, but when you think or imagine it, it's so huge. Remember, 10 to the power 10 to the power 6 is a million, 10 to the power 9 is a billion, 10 to the power 12 is a trillion. So there is 10 to the power 6 more to 10 to the power 12. So it's a million trillion electrons. It's a million trillion electrons in just 1 Coulomb. Just take a moment to, grasp this number, to grasp this particular number. It's so huge. Which means that 1 Coulomb is a very huge amount of charge. Usually, which the charges which we use in most of our day-to-day activities is in millicoulomb, microcoulomb, nanocoulomb, picocoulomb, which are smaller units of basically the same thing. So 10 to the power 9 electrons. This is NCERT exercise 1.1. Come on, every warrior should start putting up the answers in the chat box. Glad it is useful, Nanjos. But I want everybody to attend these classes, or else there will be no motive for us to conduct these classes continuously. Remember that. So if 10 to the power 9 electrons move out of a body to another body every second, how much time is required to get a total charge of 1 Coulomb on the other body? That is the question. Come on, think about this. Think about this. How we'll do this particular question? As mentioned, 10 to the power 9 electrons move out of a body every second. So to get a total charge of 1 Coulomb. Now 1 Coulomb has how many charges? Well, think about it. 1 Coulomb has how many charges? So each charge is 1.6 into 10 to the power minus 19 Coulomb into the number of charges will give me basically 1 Coulomb of charge. So the number of charges in 1 Coulomb is 1 divided by 1.6 into 10 to the power minus 19. This is the number in basically 1 Coulomb. Now, if 10 to the power 9 electrons move every second, so to get 1 Coulomb, how much time is required? So think of it this way, guys. The number in 1 Coulomb is 1 divided by 1.6 into 10 to the power minus 19. Okay, whatever that number be. If you divide this number with 10 to the power 9 whatever electrons or basically charges per unit time, basically per 1 second, if you divide this, what will you get? These many charges you need. If you divide it with these many charges per second, I will basically get the total time which is required to make these many charges flow to get 1 Coulomb of charge. Think of it this way. If you are not getting it, imagine total number of charges which I need is basically 1000, and I know that per second, example, 10 charges come per second. So how much time will I take to bring in those 1000 charges? If I divide 1000 with 10, I will get basically 100. So 100 seconds will be needed for me, because every second 10 charges come. So every second, if 10 charges are coming, if I wait for 100 seconds, 100 into 10 will give me 1000. Same way, this is a number. If I divide it with the number of charges per second, whatever I get will be basically the time. That's what they would have done. They would have divided this with this, so I will get basically the time, and it comes out to be 198 years. Guys, that's a long time. So just look at it. Even though 10 to the power 9 electrons seems like a big number, but to get 1 Coulomb of charge, it is taking me 198 years. That means I need few generations for them to conduct this particular experiment. So this just tells you how big 1 Coulomb of charge is. How big 1 Coulomb of charge is. It's not so easy. It's a very big number. So usually we deal with micro, milli coulombs or nano coulombs. Is that clear, everyone, till this point? All right. Moving on to the next one. How much positive and negative charge is there in a cup of water? Now, this example which is there in NCERT, they have assumed that the cup of water is 250 grams. Obviously, you can say why 250? I will take it as 220. So there is no, clarity on that. But just assume a small cup of water is 250 grams, then or 250 ml basically. So we know that the molecular weight of water is 18 grams per mole. So 250 grams will have how much moles? 250 grams will have how much moles? Basically, you divide 250 divided with 18, you will get the number of moles of water. Number of moles of basically water. If you multiply by the Avogadro number, which is 6.02 into 10 to the power 23, what you will get is the number of molecules. What you will get is the number of molecules in it. Is that right? Yes, you'll get the number of molecules in it. What do you do with that? Well, each molecule of the water, H2O, will have 10 electrons. Think about it. Why? Oxygen, guys, atomic number 8, right? And hydrogen, atomic number 1. So H2O. So there are 2 electrons in those 2 hydrogens and 8 electrons in that oxygen. So I would just say that 2 electrons from here and 2 protons from here. And from oxygen, you will get 8 electrons here and 8 protons over here. So if you see totally, there are 10 positive charges, and over here, there are basically 10 negative charges. So each molecule gives you 10 positive and 10 negative charges. So these many molecules will give you into 10, you multiplied by 10 amount of positive or negative charges. That many number of positive or basically negative charges. So you just have to multiply this whole number by 10. Is this point clear? Very good. Last step, how much charge is there? Now guys, every charge is 1.6 10 to the power minus 19 coulomb. 1.6 10 to the power minus 19 coulomb. So whatever number of charges you got, 8.3 into 10 to the power 25, if you multiply this with 1.6 10 to the power minus 19, what you will get is the charge of positive or the charge of negative magnitude wise as a whole in that entire 250 ml of water. If you notice, this charge is very, very huge. Look at this, 10 to the power positive 7. So many zeros. It's like 13 million coulomb of charge. If you calculate it, it is actually 13.38 million coulomb of charge in just a cup of water. But the fun fact is there is equal amount of positive and negativeness. So it is electrically neutral. They cancel out. So you don't feel anything. But even a small cup of water has this much amount of charge. That is what this example signifies. What these two examples tell you, although even small amounts have very huge amounts of charge, but in equal amounts, it's very difficult to separate them out and to just get, an unbalance of more positive or less positive. So this example shows it takes a lot of effort, lot of time, lot of energy to, create that unbalance to get a huge coulomb of charge. That is the significance of these two examples. Did you understand the meaning of these two examples? Hello, Thani, Tamil. Did you understand the significance? It's not just for calculation. See, nobody tells you while solving these examples what is the significance of it. The significance is exactly that. Even though there is huge amount of positive and negative coulombs, to create even a coulomb of unbalance takes a lot of time and effort. So that is the meaning of it. All right. So that was about charges. Shall we go ahead, my dear warriors, and let's talk about the next concept, which is basically the Coulomb's law. Yep, Coulomb's law. Okay. So now we know that there are some main properties of charges, and we saw that right over here. The charges can be added or subtracted, right? Where did it go? Yeah. Charges can be added or subtracted. Total amount of charge is conserved. And yes, the total charge is always basically quantized. It is always a multiple of the basic charge, which is this particular value. Now, let's talk about the forces between the charges. This is basically given by our Coulomb's law. So, Coulomb's law is a quantitative statement. Quantitative means where you can calculate. It gives you the quantity, the amount of whatever things you are calculating. Qualitative means I just tell you, listen, two positive charges will repel. Opposite charges, positive and negative, will attract. It's a qualitative. It's just telling the quality of that object or the quality of that particular thing. It's not telling me the exact amount. I'm not telling you how much will I repel, how much will I attract. So Coulomb law gives me a quantitative, not qualitative, statement about the force between two point charges. See, very, very important, point charges. You cannot find the force between a cube and a solid sphere using Coulomb's law unless you divide the cube and the sphere into small points and find the force between every single point pair and then add them up to get the total force. As a whole, you cannot apply unless they are point charges. Everybody agrees with this? Point charges? Yep, very good. So when the linear size of the body is much smaller than the distance, then the size may be ignored and the charged bodies are treated like point charges. So just imagine if there is a cube and a sphere, I cannot use Coulomb's law. I cannot use Coulomb's law 100% because they are very, very close right now. They are very, very close right now. But imagine this cube goes very, very far, like 5-6 kilometers away. The sphere is 5-6 kilometers away from this cube. So because right now they are very, very far away, very, very far away, now I am allowed to use Coulomb's law. I can treat this like a point and treat this like a point, and then I can apply Coulomb's law. So this is like point charges where the size may be ignored and the charge bodies are treated like point charges when the distance is very, very large, when the linear size is small as compared to the distance. Size of the sphere, size of the cube is small as compared to the distance. Okay. So this particular law says that, the force which is there, the force between two charges varies inversely as the square of the distance between the charges and is directly proportional to the product of the magnitude of the two charges, and it is acted along the line joining the two charges. What it means is, imagine there is a charge here and there is a charge here. This I call it Q1, this I call it Q2. This charge and this charge will have some force of attraction or repulsion depending on their signs. That force is inversely proportional to the square of the distance between them. This is the distance between them. And it is also proportional to the product of the charges. So proportional to Q1, Q2. And that force which I am showing, this particular force, always acts along the line joining the two charges. Meaning the force won't be like this. The force won't be like this. It will be always along the line joining. Matlab, it will be either like this or like this, depending on attractive or repulsive. It will always be on that line joining the two charges. It can't be in some random direction. Is that clear? So when you combine both of them, it is directly proportional to Q1, Q2, inversely proportional to R square. You will see that the force is some constant into Q1, Q2 divided by R square. This particular constant that you are seeing, we'll be talking about it. So this is our constant of proportionality. Proportionality, which is basically called as our Coulomb's constant, because this law is given by Coulomb. This law is given by Coulomb. Okay, so that is the a formula. That is something which you are obviously supposed to remember. So let me just block this off. Let me just block it off. Yes, some constant into Q1, Q2 by R square. Now, what is the value of that particular Coulomb's constant? We will see that the value of the Coulomb's constant K is 9 into 10 to the power 9 in SI unit. This is another value which you should remember. 9 into 10 to the power 9. Very, very important. While the original okay, fine, Coulomb's law will magnitude, or in fact the other way around, Coulomb's law can now be employed to furnish. Okay, don't have to worry about these things. These are not important lines. They are just telling the history that this law can be used to define the unit of charge, not the other way around. Not important so much. Okay, ignore it. SI unit of the value of Coulomb. Okay, unit of charge that results from this. So this particular paragraph tells you how you can define a Coulomb, etc. When imagine you take two charges, 1 Coulomb each, or let's say unknown charges, and they are separated by exactly 1 meter, and I see the force of attraction or repulsion between them is, imagine, 9 into 10 to the power 9, 9 into 10 to the power 9 Newton, 9 into 10 to the power 9 Newton. Then each of these charge must be 1 Coulomb. Then each of this charge must be 1 Coulomb, because it kind of makes sense. Look over here. This is 1, this is 1, this is also 1. 1 into 1 divided by 1 square is 1. So K will become equal to F. So the force is 9 10 to the power 9. K is also 9 10 to the power 9. This can only happen when Q1, Q2 is 1, 1 each, assuming R is also 1. So that is how you can define a Coulomb using this particular law. Is that right? Okay. I hope this is absolutely clear, everyone, till this point. Yep. Okay. So here the main takeaway is the choice of K determines the size of the unit of the charge. Determines the size of the unit of the charge. Because if you change the value of K, then Q1 and Q2 will be defined different. Because Newton is already defined. What is 1 Newton? When you take 1 kg mass, accelerate by 1 meter per second square, the force acting is 1 Newton. Distance already defined. This much length is 1 meter. So if somebody chooses a different set of units, K will be different, Q will be also different in that new unit of system, some Pandu system of unit. That is the main takeaway. Okay, but it's okay. We are mainly focusing only on SI unit. Otherwise, that statement will make sense. Okay, now this particular thing I have already explained over here. That is already done. So what is 1 Coulomb of charge? Alternative definition: when the distance is 1 meter and the force which is experienced is of 9 into 10 to the power 9 Newton. Now this particular Coulomb constant which you saw over here, this Coulomb constant, that is also written down as 1 by 4 pi epsilon naught. The Coulomb constant K is also alternatively written down as 1 by 4 pi epsilon naught. So you can remodify the same law which you saw over here and write it down as, instead of K, force is 1 by 4 pi epsilon naught Q1 Q2 by R square. What is this modification for? You will understand it later on when you study dielectric material. But when you write it like this epsilon naught which you see over here, this epsilon naught is basically called as the permittivity of free space or permittivity of vacuum. And the value is basically 8.85 into 10 to the power minus 12. This permittivity of free space is basically medium dependent. Medium decides that. It tells me how much electric force, is permitted in that particular medium. How much electric force is permitted in that medium. Right now, most of the times we use air or vacuum. Just like you might have studied, refractive index of air is roughly 1, same like vacuum. Same way, if you conduct the same experiment of two charges in some water, you get very irritated, you drown those charges in water, the force will change because the medium has changed. So this value will change. Epsilon naught will change. It will no longer be this, it will be something else. It will be permittivity of the medium, not of free space. Because free space means vacuum, or basically almost like air. Almost like air. Is that clear? Okay, so we have Diksha ma'am over here in the physics class. Welcome, Diksha ma'am. Yes, I hope you guys have been attending all the classes of all the NCERT lines by all the teachers, guys. Already, most of us have done or almost done 2 chapters in NCERT lines. Very good. Nice to see all the Josh. Good evening. Good evening. Great. So, till this point, I hope it is clear what is the meaning of permittivity, how much field or how much force is permitted in that medium. Electric force is permitted in that medium. That is what this decides. If the medium where the charges are placed is different, this value will definitely change. Now, there is this vector form which is pretty useless, I feel, but still we'll just write about it, or we'll just talk about it. How do you write the Coulomb's law in vector form? I'll teach you a simple way. The final formula is here. So I'll just tell you a simple way of noting this down. See, imagine there is a charge 1 here. Imagine there is another charge over here. Let's say there is some distance between them. And charge 1 on charge 2 applies a force. So this is the force on 2 due to 1. Same way, charge number 2 on 1 will apply some force. So I will write it as force on 1 divided by 1 because of 2. This force, either this or that, the magnitude of the force we have already seen. It is basically k times q1 q2 divided by the distance square. We have seen that. But when you write it in vector form, remember, any vector quantity is nothing but the magnitude, and then you have the unit vector. Always. A force of 5 Newton I cap, a force of 7 Newton J cap. If it is in some other direction, that whatever magnitude, 78, n hat. N hat is the directional vector of that particular vector quantity. It is having a magnitude of 1. It is just used to signify the direction. So same way, think about it. If I tell you, I want to find the force on 2 because of 1. How about showing a vector called R21, which is nothing but the position of 2 with respect to 1. Remember, in 11th standard vectors 1D, 2D motion, you have studied this. Position of 2 with respect to 1 is R2 minus R1. Velocity of 2 with respect to 1, V2 minus V1. Acceleration of 2 with respect to 1, A2 minus A1. Champa's velocity with respect to Pandu, Champa's velocity minus Pandu's velocity. This is the pure definition which we have seen even in relative motion vectors everywhere else. So, if I define a small unit vector over here, something like this, which is R21 hat, R21 hat, it is just a unit vector. It's the same as the direction of this force. Hence, can I not say F21 bar, this is the vector, is magnitude. Magnitude is K, Q1, Q2 divided by distance. Distance is this, which is R21, which is basically R21 square. Unit vector. What is that unit vector? It is this one. So it is R21 hat. This is the vector form of Coulomb's law. This is basically the vector form of Coulomb's law. Alternatively, if somebody asks me what is F12, also F12 will be the same thing. It will be K, Q1, Q2. This is distance. Now whether you write R21 or R12, it's one and the same thing. R21, R12 square, and here it will be nothing but R12 hat. R12 hat. Just like R21 and R12, the order will change. The order will change. Think about it. This thing over here, technically is negative R21 hat. Everything else is the same. The magnitude is the same. It has the same magnitude. It has the same magnitude, but the direction will be opposite of 21, which means F12 bar will be technically negative of F21 bar. These two forces are magnitude wise same, but direction wise they are opposite of each other. It has to be, because Newton's third law, if a body applies a force on another body also applies the force on the first body. These forces are opposite, equal, but act on different objects. If one is called action, the other is called reaction. So this is Newton's third law. Make sense? Make sense, everyone with me on this? Perfect. So this is exactly what has been explained over here also. If you notice, F21 is 1 by 4 pi epsilon naught Q1 Q2 by R square R21 bar. So same formula has been written down right over here. And if you are wondering how do I find R21 cap, basically any unit vector can be found using this definition. Any vector cap is the vector itself divided by its magnitude. A hat is A bar by A magnitude. V hat is V bar by V magnitude. That's how you find any unit vector definition. That is what has been mentioned right over here. R21 cap is R21 vector divided by the magnitude. So this is basically the vector. This is basically the magnitude. Keep this in mind. Okay. Rest everything else, whatever I had written before also, R21 is R2 minus R1. Same thing is written over here as well. Clear? Is this vector form absolutely clear? Yep, awesome. And because F12 is negative F21, what does this tell you? F21 is basically equal to negative F21. This just tells that it is consistent with Newton's third law. Action, if one is basically action, the other is basically reaction, equal and opposite. I have also mentioned that now we are not worrying about the medium so much. We are just considering them in vacuum. If they are placed in some another medium, then we'll be studying that later on. Remember, I had just mentioned about permittivity. That permittivity value will change. Where is that permittivity? Yes, this permittivity value will change depending on the medium being present. Right now, we are not worried about it. So this is not an important line. Let's talk about this question. Yes, Saran, will be doing laws of motion after next week. We'll be doing kinematics in 2D and then we'll be starting off with laws of motion in our RNA series. Okay. So Coulomb's law between two charges and Newton's law of gravitation, both are having similar looking format, because for electrostatics it is 𝐂𝐤 𝐤 divided by R square. For gravitation it is 𝐺𝑚1 𝑚2 divided by R square. R square is there below, product is there on the top, constant is there outside. So since their laws are very similar, question is to compare their forces for I think electron and a proton. Estimate the acceleration of electron and proton due to the force when they are 1 angstrom apart. Okay, masses of proton, electron are given. Okay, compare the strength of the forces by determining the ratio of their magnitudes. Okay, so basically over here, the first part is for 2 protons and second part is for 1 electron and 1 proton. Okay, see, if you divide force of electrostatics divided by force of gravitation, it will look something like this. K, charge on the electron or charge on the proton is the same thing, which is E only. I'm just interested in the magnitude. divided by r square. Similarly, gravitational force will be G, mass of the proton or mass of the electron. So m1 m2 divided by r square. So r square will cancel. So it will be k e square by G m1 m2. When it is basically scenario number 1, where is it? Scenario number 1. For an electron and a proton, this masses will be these ones. One will be 1.67 into 10 to the power minus 27, and this mass will be 9.11 into 10 to the power minus 31. These electrons or protons charges will be the same thing, 1.6 into 10 to the power minus 19, and this will be whole square in the first case. In the second case, for two protons, it will still be the same. It will still be the same. This will be the same thing, whatever I have written down over here. This will be different because there are two protons. First mass will be this one. The second mass will be exactly this one, 1.67 into 10 to the power minus 27. So we'll get two different answers. So basically, you will get two different answers. The ratio of the electric force by the gravitational force in the first case versus the ratio of electric force upon the gravitational force in the second case. These ratios after calculations comes out to be, I think, this one, 2.3 10 to the power 39, 2.3 into 10 to the power 39, and for the other one it comes out as 1.3 10 to the power 36, 1.3 into 10 to the power 36. What does this example tell you? See, it's not about calculation. It is telling you something. It is telling me electric force is so stronger, whether you take electron, proton, as compared to the gravitational force. It is much stronger, much stronger as compared to, gravitational force. This is the significance of this particular example. That is why when you draw the free body diagram in most of the electrostatic problems, you never show the gravitational force, or you are not bothered about gravitational force between electron, proton. Isn't it amazing? Yep, that is the significance of this. There is a second part also. Find the acceleration of electron or proton. So if you know the force divided by mass, you will get the acceleration. I think that is what is done later on. I know the force. The force, interestingly, look at it. The force, okay, between electron, proton or proton, comes out to be very small. Very small if you substitute the values. K, Q1, Q2 by R square. Charges are 1.6 10 to the power minus 90. And the distance they have taken it as 10 to the power minus 10 meters, which is 1 Armstrong. It is very small. So then you'll be like, sir, fine, you said electric force is very strong as compared to gravitational force. But the electric force only, sir, look at this, it is so small. Then should we even bother about electric force? Do you get my point? Electric force is strong as compared to gravity. So fine, we neglected gravity. But electric force itself is so small. So why should we even worry about electric force? That reason comes in the next step. If you divide the force by mass, you will get acceleration. Mass is so small that the acceleration comes out to be very large. So even though the force is small, the mass being so small, the acceleration produced becomes so huge that you need to consider the electric force. Got it? Understood the significance of this particular example, my dear warriors, my dear lions? Shall we go ahead? Yep. All right. There is another example which is there. Let's have a look at that. Yes, Krishna, acceleration is very large. Now, talking about the next example, there is a charged metallic sphere which is suspended by a nylon thread another charged metallic sphere held by an insulating handle brought close. So there is a sphere here, there is a sphere here. You are holding it using an insulator so that the charge does not go out or go in, and you are placing it 10 centimeters away from each other. So there will be some electric force between them. So there is some deflection. So the repulsion is noted, okay, by noting the deflection in the shadow. So they are using light. So because light falls on that sphere, there is a shadow. The shadow will move some amount. So noting how much the shadow moved, they are able to find how much the deflection is, and thereby estimating the force is so much. Now what you do is these spheres are touched by uncharged spheres. These both are touched to two identical uncharged spheres. So what will happen immediately? Imagine, yeah, imagine if this had a charge q, this will become q by 2, this will become q by 2. If this had a charge of capital Q, this will become now capital Q by 2, capital Q by 2. The charges will get divided now. And now you take away those C and D separately away from each other. Now you bring back those A and B spheres. Because the charges have reduced, the force will reduce. So you reduce the distance and make it 5 centimeters. Now what will be the new force between them? You have to compare. You have to basically compare the old force versus new force. If you observe carefully, originally, whatever the force would be there between them, F naught, okay, F naught, that F naught will be K Q Q divided by R square. Later on, what happens? When you touch uncharged sphere, the charges become half and you bring them back over here. The new force will be, let's say, F1. The new force will be, let's say, F1. Remember, the charges are also halved. The charges are also halved. So what is that new force? K Q by 2, Q by 2 divided by distance. Instead of R, it is now R by 2. So I'll put R by 2 whole square. Interesting thing, 2, 2, 2, 2 cancels. You will still get it as K Q Q divided by R square, which means our new force just happens to be equal to the old force. It just happens to exactly equal the old force. So the force hasn't changed. So the electrostatic force remains unaltered. It is the same. It is just coming out to be as F. That's what this example is all about. I hope before this, if you never understood what is happening in the example, now you have understood. So there were two spheres. They were individually touched to some uncharged bodies. So the charges will get distributed equally because they are similar. Now those spheres will repel less. So you bring them closer. So it so happens that even if the charge reduced, the distance compensated for it and they ended up attracting by the same amount. That is the significance of this particular example. Cool. Let's move to the next question. Now, we studied how to find out the force between 2 point charges. What if there are more than two charges? 3, 4, 5, 6. That's when you use this particular principle. Okay. When there are more charges like Q1, Q2, Q3, Q4, Q5, etc. and there are many charges which will keep on repelling or attracting each other, to find the net force, what you do is basically you just add them vectorially. That's what it says. This is exactly the principle of superposition. So what they have done, in order to find the force on one due to 2 as well as due to 3, you first find the force by 2 on 1, which will be here. You find the force by 3 on 1, which will be here. These are two vectors. Using parallelogram, triangle, polygon, you find the resultant vector. That is what they have done. So they found force 1, 2, force 1, 3, and then add them vectorially to get the net force. They have written it down in vector form, but when you actually do it, it is much more simpler. So this is exactly the principle of superposition. So the principle of superposition says that in a system of charges, in a system of charges, the force on one due to Q2 is the same as given by Coulomb's law, and it is unaffected by the presence of other charges. The total force on any charge is due to all the charges and is just given by F1 plus F2 plus F3 like that. That's it. So you just do vector addition. Vector addition. You should not think that, sir, this charge came, sir. So will this charge affect this charge's force on this? No. This is Champa. This is Pandu. This is Laddu. Pandu loves Champa. Laddu loves Champa. Just because Pandu loves Champa, Laddu won't say, I will love you less. They are not affected by it. Pandu loves Champa irrespective of whether Laddu loves Champa or not. So they are unaffected by the presence of other charges. Everyone together will love Champa. So Champa will experience net force. Champa will experience the love from everywhere. So that is what has been mentioned here. So in a system of charges, the force on 1 due to 2 is the same whether other charges are there or not. The love of Champa, the love towards Champa will be there. Whether other person is loving or not, I don't care. And in fact, Champa will experience the love from everyone. The force by all the charges together will be applied using vector addition. As simple as that. Okay. All right. Cool. Shall we do some questions? Okay. So here are the questions. Consider three charges Q1, Q2, Q3. Okay. Each equal to Q on the vertices of an equilateral triangle. What is the force on charge Q which is placed at the centroid of the triangle? Now, in this particular question, if you look at the solution, you will break your head. What the hell have they done? Really, I mean, this is so stupid what they have done. The solution, it was unnecessary. Isn't it like obvious? If this charge, this charge, this charge are equal, this charge will give a force here. This charge will give a force here. This charge will give a force down. It will be basically, they will cancel. The net force will be 0 because this will be 120, this will be 120, this will be 120, this is F, this is F, this is F. Net force is 0. So the net force on this will be 0. That is what they have actually found out. It is 0 by doing all this nonsense. They have written it down in vector form. So guys, just because you learn something does not mean you have to apply it. This is a very classic example of that. Chumma, say, they wanted to show off that, okay, listen, I taught you vector form for a reason. Remember this vector form? Where did it go? It's somewhere here only. Some crazy looking vector form. This is useless. I mean, most of the times you don't need it. Most of the times you don't need it. You can just do it by parallelogram law. In fact, they have said that also. Parallelogram or triangle law, using triangle parallelogram law, addition of vectors, and Coulomb's law, you can solve most of the problems. You will be able to, all electrostatics is basically end of the exactly that. So, you know, using vector form is a bit of a show off. So this is basically a show off. Remember that. Cool. Otherwise, you don't need it. Even for the next exam, answer is 0 for this. Even for the next example, I won't use vector form. I won't use vector form. Why? Because what is there? Instead of Q, Q and Q, there is Q, Q and minus Q. Okay, no issues. Think about it for this particular charge. What will you do versus this particular charge? This is a negative, this is positive, this is negative, this is positive, negative, positive will attract. So 100% there will be some attractive force. Let's say I call it F1. This will, or let's say I will call it as X. This also X force. Okay. These two together will produce a resultant. These two together will produce a resultant over here on the charge at basically C. On the charge at basically C. And remember, the angle between them is basically 60 degrees. This is an equilateral triangle. So I just can say FC is nothing but a root of what? A square plus B square plus 2 into A into B into cos of angle between the two vectors. So x will come outside. I have one remaining here, and over here 2 cos 60 is basically half. 2 into half is 1. So 1 plus 1 plus 1 is root 3, where x is nothing but the force between this and this charge, which will be k q q divided by, this is just the magnitude, divided by the distance. Whatever is the distance, let's say it is L. So L square. So it is magnitude wise kq square by L square multiplied by root 3. You will get the force on the charge kept at the vertex C. Isn't it simple? Isn't it simple, my dear warriors? Similarly, think if I want to find the force on this point, on this charge over here, I will look at it like this. This positive and this negative will attract definitely each other with an amount x. Positive and positive will repel. So the repulsive force will be here. Amount will be still x. Magnitude will still be x only. Because charges magnitude are same, distances are the same. So x will be nothing but k q q divided by L square, which is k q square by L square still. But the resultant now will be over here, the resultant, and this angle will be 120. So fine. So the resultant force at point A will be root of x square, which is a square plus b square plus 2 into a into b into cos of 120 degrees. So x is common, take it outside. 1 plus 1 minus 2 into 1 by 2. Why minus? Because cos 120 is negative half. 2 becomes 1, 1 minus 1 is 0. So it will become x root 1 plus 1 minus 1, which is 0. So x root 1 is basically x. So x is nothing but this whole thing. So you can find the force on A very simply by using your original old formulas which you have learnt in 11th standard for vectors. If you notice what they have done over here, you will break your head again. They have tried to find the answers using vector addition and all of that. That is not needed at all. Is that okay, everyone? That is not needed. Cool. Awesome. They have also mentioned one more thing. If you add this force, and this force, which will give you the total force on all the three charges together, that answer will come out to be 0. It kind of makes sense. It kind of makes sense because this is the net force on the system. The net force on the system, that will be 0 because all these forces will be actually internal forces. Internal for the particular triangle. These three charges attracting, repelling each other is an internal force. Internal forces will always cancel. So you will see that the net force will be 0. Okay. They will not produce any resultant as such. Kind of makes sense. Yeah. For FB also, it will be the same thing. Very good. Somebody is asking, sir, can you solve for FB? Just think this positive and this positive will repel. It will be here. This positive and this negative will attract, it will be here. So the resultant of both of them will be here. Isn't this diagram the same as this diagram, just mirror image? This is same as this, and obviously the angle between them is 120. Reason is just like this particular internal angle was 60 over here, this internal angle is also 60. So this external angle is 120. So the same logic applies and you will still get the answer as, x, which is kq square by L square. Got it? Trisha? Absolutely clear? Very good. Awesome. Let's move ahead. Let's move ahead. Let's talk about electric field now. Let's talk about electric field. So we have talked about electric force till now. We have talked about charges till now. We have talked about forces formula in Coulomb's format and also superposition. How and more than one charges are there. How you find the net force by adding them like simple vectors. Nothing great. Now, let's talk about electric field. Let's talk about electric field. Just imagine Pandu and Champa love each other. Pandu and Champa, fall in love with each other. Pandu attracts Champa. Champa attracts Pandu. They are very attractive, hot people. Okay. So, When Pandu saw Champa passing the other day on the road, Pandu fell in love for Champa. Pandu started moving towards Champa. When Champa saw Pandu the other day, and she saw Pandu is such an handsome guy, she also fell for him and she started moving towards Pandu. So, as a whole, imagine they did not see each other. Pandu and Champa individually also, they are good looking, amazing people, hot people, right? How did Pandu know that I have to attract Champa, or Champa I have to move towards her, or how did Champa know that okay I have to move towards Pandu? Maybe they are sending an aura, they are sending some signals around them. Even when Pandu is walking around alone, he ends up attracting, or he ends up grabbing that attention. Even when Champa is walking alone, she ends up grabbing that attention because she's beautiful. So imagine same thing for charges. Imagine there is a proton and a proton, or a proton and an electron. Proton and electron will attract each other. How did this proton know that this electron was here? How did this electron know this proton was here and I have to get attracted? So even when this electron was not there, only this proton is going, he had some aura around him that anybody who comes close to me, I will either attract or repel you, depending on your sign. Same thing. This electron also thought, I also have an aura around me. I will also attract and repel anybody around me depending on the sign. If you're positive, I'll get attracted. If you're negative, I will not get attracted. Same thing happens with charges, guys. And that aura which is there around them is called as the electric field. That is what you will see has been explained throughout this paragraph or the next maybe. So the definition, the formula for electric field due to a point charge is given over here. We'll talk about the units and everything over in a bit. If you have a charge like so at a distance r, you are not placing any charge. There will be an electric field at that point. The value of that electric field magnitude wise is k q divided by r square, which is 1 by 4 pi epsilon naught, just q by r square. Notice how the second charge is not present at all. They have just mentioned this in vector form. So in vector form, it will be 1 by 4 pi epsilon naught q by r square r cap. That is vector form. I mean, such a useless thing. This is magnitude, this is unit vector. Okay, so they have mentioned the vector form. This is vector form. Usually, what we'll be needing is the scalar form. What we'll be needing is basically the scalar form, which is exactly what I have put over here. This is what we'll be needing most of the times. Okay. Now, here they have exactly mentioned this. We may ask the question, if the charge q is removed, then what is left in the surrounding? Imagine there are two charges. One of the charges removed. What is left in the surrounding? Nothing, except for that single charge. But if there is nothing at point, how does that force acts when we place a charge at that particular point? So there must be some kind of aura or some information or something which is still around that charge, which tells, hey, listen, I am a positive charge, I am here. The moment you come over there, I will be attracting you or I will be repelling you. So that is basically the concept of field. We say that a charge q, produces an electric field everywhere in the surrounding. Very, very important. A charge which is there produces something called as an electric field everywhere in the surrounding. And when another charge is brought at some point, the field there acts on it and produces a force. Very important. If I am a charge, I will produce a field around me. I have nobody to attract, but I'm telling everyone, hey, listen, I am hot. Listen, I am handsome. Listen, I am amazing. If somebody comes, they'll apply a force, attractive or repulsive, depending on the thing. Okay. So this is exactly what has been mentioned over here. Cool. Every till this point, clear? Is this lecture 1 of 12th? Yes, Nihara, Niha. Yes, it is. Yeah. Now, okay, how, yeah. So once you know the field, you can find out the force. Remember, the force formula was the same thing, just you multiply by the q. You multiply by q. So if you know the field, to find the force, you just have to multiply it by the charge. That is what it says. So say for example, there is an electric field which is being created, and you happen to place some charge over here, then the force which acts on that charge, the force which acts on that charge is just given by the charge value, is just given by the charge value multiplied by the particular field. That is exactly what has been mentioned over here. Okay, that is exactly the same thing, guys. So if you take a charge, place it in a field, the force acting is the charge multiplied by the field. Now, remember, field is actually a vector quantity. Okay, field is a vector quantity, and the SI unit you can see will be Newton divided by Coulomb, so Newton per Coulomb. So the SI unit of electric field, the SI unit of electric field is Newton per Coulomb. Also, it is a vector quantity. It is a vector quantity. Keep this in mind. Why is this star mark placed here? Maybe because I think later on you will see there is another unit of electric field, which you will learn later on. Also volts per meter. Okay, or volt per meter. You will see that later on. Don't have to worry about it right now. Both are fine. Yes. Okay, amazing Gopika ma'am is also here. A for amazing Gopika. Very good, guys. Keep it going. Keep it going. Now that we have understood what electric field is, we will also formally define it, because see, whatever formula I wrote over here is the electric field due to a point charge. But in general, it might not be a point charge. It might be because of many charges together. You are trying to find the field. So in those cases, the actual definition of electric field is this one, where maybe there is a collection of charges, maybe some many charges are there, positive, negative, doesn't matter. This is creating some electric field. To find that electric field, what you do is you bring in somebody to test how much field is there. This q is also called as your test charge. That is what has been mentioned. Okay, and the charge q, which tests the effect of the source charge. The source charge is basically this one. This green one is basically the source charge, which is producing the electric field, which is called as the source charge. This is creating the field. You are testing it using that small q, okay, which is also called as your test charge. Now, in order to find the field, what you do is you first check how much force this charge is experiencing and divide it by that charge, divided by the charge. That force per unit charge, that force per unit charge is the field. That force per unit charge is the field. But there is a small problem in this. There is a small problem in this q also apply a force on this capital Q, because of which this charge might start moving somewhere here and there, which will produce undesirable effects. So what you do, you make this Q very, very small. That is why you see this limit Q tends to 0. Why? Because if this charge is small, then it will hardly affect this charge. So this will stay stationary, no undesirable effects. That's why you see this limit over here. Okay, so make q negligibly small. So q is made negligibly small so as to remove that difficulty, okay, where q itself is bound to the experience of an electrical force due to q. That difficulty you get rid of by making that small charge very, very small. Is that clear? Everyone understood this concept? Yes. Awesome. Awesome. Now, Till this point, if it is clear, uh, there are some more points which are mentioned. Let's go through it one by one. Even though the field is defined in terms of test charge, it is independent of Q. This is because F is proportional to Q. So yeah, listen in what they mention in this particular point number 2. In this definition, it seems that electric field depends on the test charge, correct? Because you might think, sir, if I take more test charge, sir, will the field change? Remember, I'm testing it. So whatever field is being produced cannot depend on what I'm using it to test. I might use A, I might use B, answer should remain the same. It is independent because the force itself has charge in the numerator. So that and charge gets cancelled. That's why E comes out to be independent of Q. That is what this explanation is. That is what this particular paragraph, point number 2, tells you. The electric field due to is basically depends on the Q itself, but the ratio F by Q does not depend, does not depend on the Q. Okay, the force does not depend, force by unit charge does not depend on Q itself, because F itself is proportional to Q. F itself has Q in it, Q gets cancelled. So the only thing which the electric field depends on is how far you are and what is the source charge. That's what they have said. So the electric field due to Q only depends on the space coordinate R, basically how far you are, and what is the charge value. Okay, that is something which is mentioned in this paragraph. For a positive charge, the electric field will be outward. For a negative charge, the electric field will be inward. Makes sense. If you take a positive charge, the electric field will be outwards from the charge, because this positive charge will apply forces in this particular direction on the test charges present around it. But at the same time, if you take a negative charge and you test the force around it, it will always be towards the negative charge, which means for the negative charge, the electric field will be towards the negative charge. That is what this particular point number 3 is all about. Since the force on charge Q due to charge capital Q depends only on the distance, okay, the magnitude of the electric field will also depends only on the distance. As the equal distance, the magnitude of its field are same. The magnitude of the electric field due to a point charge, the same on a sphere with point charge. Okay, so what it says is basically, if you take a charge, and you measure how much field is there over here, you go the same distance in any other direction, you measure the field here, you go some other distance, same distance, and measure the field here, this field will be same here, here, which means if you consider an hypothetical sphere, on that sphere, everywhere the field will be the same. On that sphere, everywhere the field will be the same. That is what this means. Same magnitude of electric field at the same distance, but the directions will be different. Okay. So here I would say that at equal distances, from the charges, the magnitude of its electric field is same. So thus on a sphere with a point charge at its center. So the electric field, the magnitude of the electric field is the same on a sphere. This is the same on a sphere where the point charge is at the center of that particular sphere. That is what the fourth point is talking about. Makes sense. Awesome. Pandu is also here. Harshi, I'm not so sure when I will start this in RNA series, because RNA series I'm right now prioritizing at least till Newton's law circular work power energy, because these are some main concepts which are needed for your 12th standard concepts. So at least till work power energy and circular motion, let's do in RNA series first, and then let's come to 12th standard. What's it? Okay, FBD, etc. You will need all those things. Now, remember, due to a point charge, the electric field formula was this one, which I just gave it to you over here. If there are 3, 4 charges, then all these charges will create their own field around them. So there will be a resultant electric field at any given point in space. There will be a resultant field at any given point in space. Agree with this point? Everybody with me? Okay, perfect. So what is that particular resultant field is given by, where is it? Superposition principle again. Yep. So remember superposition principle, then same thing. Superposition principle can give you the resultant field, resultant field at any point by just adding all of them. By just adding all of them. That's it. Adding all the fields. E1 plus E2 plus E3 plus En. You add them, you will get the resultant field. Simple. At any particular point, field due to 2, field due to 1, field due to 3, field due to 4. You take all these vectors, find the resultant, you will get the net field at any point. Very simple, very straightforward. This paragraph is very, very useless. I mean, unnecessarily lengthy. The main takeaway is that superposition principle can be applied even on electric fields, just like electric forces. That's the main takeaway of this. You don't have to by heart any of this. Okay, you don't have to by heart any of this. Just remember, since electric field is a vector, you will just add them like vectors. Add them like vectors. That's all. Okay, cool. Sir, in ER, R indicates the distance. So what they mean over here is, if I take this point, okay, one field is here, another field is here, another field is here, another field is here. This is having some position vector. This is going, if I add all these things, together, I might get a resultant electric field. At this point, this is having a position called R, position vector R. So that is why it is called ER. If I choose some other position, let's say over here, some other position here, then the same electric fields due to all the charges around might be in different directions of different magnitudes. Now again, when I find the resultant, it will be E of R. This R will be this over here. So wherever you are, depending on that, since other fields will change, hence the resultant field will change. That is what it signifies, which is very obvious. They just make it look complicated at sometimes, So that is why I am conducting this series, because I want us to decode that NCERT. I want us to understand the NCERT in a much simpler manner. Is that clear what that E of R means? R stands for the position. If you change your position from here to here, obviously my field will change because I will be affected differently from all the charges. If I shift my position here, I will now be affected differently. My net field will change. So distance plays an important role. That is what they have in fact mentioned. So as E vector varies from one point to the other, one point to the another in space. So you will have to consider that location of that particular point. Clear? Uh, Taswin, I will do all the chapters only on one condition. If I see clear-cut attendance and clear-cut support for the series, or else I won't hesitate to stop any series. Let me tell you that. I will just do whatever you guys like, because if I see that, okay, you guys are liking a certain kind of lecture, I'll be doing exactly that. It's very simple, guys. Okay, so I need your support. I want you to promote this video, this channel, these teachers, all the teachers on this channel in your school or wherever, vicinity, society, friends circle, friends group, WhatsApp group, Telegram group, Instagram group, whatever. You need to tell, listen, there is a set of teachers who are teaching all the students who never got NCERT line by line in English. In Hindi, it might be there. Many channels are there, and many students also support those channels. I want that same support from all the students, especially in South India, especially in Northeast, especially outside India. listen, there is a channel which is doing, the only channel which is doing this. So we need to attend that. We need to show our support, just like many students show support for, other channels in Hindi or any other language. So only when that happens, we will continue. Very simple, guys. Yeah. Okay, great. Let's move on to the next concept. What is the significance of this electric field? Well, let me tell you, over here, they say, you might wonder why the notion of electric field has been introduced here at all. After all, system of charge is a measurable quantity force which can be directly determined. Why then introduce this quantity? Okay, for electrostatics, the concept of field is very convenient, but not really necessary. Electric field is an elegant way of characterizing the electrical environment of a system of charges. Field at a point in the space around the system of charges tells you the force a unit charge would experience at that point. The field is a characteristic of the system of the charges and is independent of the test charge that you place. The term field in the physics generally refers to a quantity that is defined at every point. To point, electric field is a vector, since force is a vector, blah, blah, blah. And then they give this big paragraph over here. Take your time to read this. I'll read it if you want, part by part. The true physical significance of the concept of field, however, emerges only when we go beyond electrostatics and deal with time-dependent electromagnetic phenomena. Suppose we consider the force between two distant charges, blah, blah, blah. Now, the greatest speed with which a signal information can go from one point to the another is the speed of light. Sometimes I feel the authors in NCERT wanted to just chumma show off something by writing some complicated statement, but actually it is very unnecessary, number one. Number two, it is very simple. I'll tell you what this entire thing means. See, if I want to find force between two charges over here, correct? If I want to find force between two charges over here, I'll chumma say, using Coulomb's law, F is K, Q divided by R square. I mean, I will hardly do, oh, let me find the field at this point due to Q. And I will be like, oh, it is KQ divided by R square. Oh, wait a minute. I am placing a charge over here, Q. Oh, so the force on that charge will be Q into E. What is E? It is KQ by R square. Hence, it is KQQ by R square. Answer is the same. So you might wonder why even this field concept is necessary. That is what initially they have mentioned. You may wonder why. You may wonder why the notion of electric field has been even introduced at all. Okay. You can do this using Coulomb's law. And electrostatics, this is very, electric field is convenient, but doesn't feel very necessary. But they say that, listen, electric field is an elegant way of characterizing the environment around it. And it tells me the characteristic of the system of the charges and is independent of the test charge that you place. The term field in physics generally refers to the quantity that is defined at every point and may vary from point to point. And the field is a vector since force is a vector. And then they give this big paragraph over here. Here, till now, you might have understood that I didn't have to define field. Even with Coulomb's law, I could have solved the problem. The reason why we define field seems unnecessary, does not seem necessary, but okay, we can do with it also. But the real reason why the field is there is because it gives you a complete understanding of the system of charges, even without this charge being present. Fine, now this charge was there, that's why you are able to calculate the force. But let's say this charge was not there, then only this charge is there. It will tell me how the region around it behaves, what is the presence of this charge here at different points in space. So if tomorrow, instead of placing this charge here, you place this charge here or here or here, then it will be affected differently. The force will be different, the direction will be different. So the field is basically telling us how the surrounding behaves or what presence might be felt due to other charges, how much force exists per unit charge in that entire region. So that is where the field notion comes. And then they say over here, this is not a part of the syllabus. Basically, imagine, imagine, imagine I take this charge. There is a charge here, there is a force here. I take this charge little bit more far away. Don't you think the force will become less? Here the force will be more because the distance is far. Here the distance is close. So do you think if I move this charge, immediately the force on this charge will become less? Do you think it will immediately become less? Yes, Dream 11, Dream 1, I'll be doing it. I'll be conducting a special class to talk about roar on J. Do you think if I move this charge immediately here, immediately the force will become less, or will there be a small time delay? The answer is yes, there is a small time delay. It takes some time for the force also to travel from here to here. So the concept of electric field helps us understand the time delay process. And when you move the charges, the time delay encountered in knowing how much time it takes for the force to change, that helps us in electromagnetic phenomena. And there are many special theories like electromagnetic radiation by Maxwell due to moving charges and blah blah blah. So these two paragraphs, my dear warriors, complete waste. Don't worry about it. Just that few lines which I have marked, just go through that. And the main takeaway here is that uh, it the uh, the information of any charges motion is not instantaneous. There is always a time delay. That is what they have mentioned. So the effect of any motion of q1 on q2 cannot arise instantaneously. There will be some time delay between the effect of the force onto, and this happens because any information that flows can't flow faster than speed of light. Nothing can move faster than the speed of light. Even that information that, listen, I have moved, so the force will reduce, that charge will know only after some time. That is what this mentions. Okay, so this paragraph not so important. All right, but chumma they have given to complicate things, so I ended up explaining it, but otherwise not so important for NEET at all. Okay, correct. All right. Now, moving ahead, an electron falls through a distance of 1.5 centimeters in a uniform electric field. This much magnitude, the direction of the field is reversed, keeping the magnitude unchanged, and a proton falls to the same distance. Compute the time of fall in each case. Guys, see, whether it is electron or proton inside the field, the force on it will be the charge into the field. Charge is basically E. So acceleration due to gravity, which is force by mass, will be EE by m. Now the time to fall using S is equal to ut plus half at square. Since it is falling, starts to fall, u will be basically 0. So S will be, let's say, what is that? Falls to the same distance d. So d is basically S. Half into acceleration. Acceleration is EE by m into t square. So moving this around, t will be nothing but d into m by EE, the whole thing under the root. So this is a time to fall either for the electron or for the proton. What you can see, d is same, E is same, E is same, mass is different. So mass of the proton is more, so time taken will be more. Mass of the electron is less, so time taken will be less. As simple as that. Substituting the values, you will get the times also. So they have found that out. The time taken for the electron, this is for the electron, okay, is this much nanoseconds. 2.9 nanoseconds is very small. And for the proton, it is this much. It's slightly more because proton is heavier. This is for the proton. Okay, you can see that the time taken are different. Interesting thing, we have neglected gravity. Why we neglected gravity? Because Gravitational force is much weaker as compared to the electromagnetic forces. Electromagnetic forces are stronger. The interesting thing about this NCERT example is that had you used the normal formula for free fall, which was root of 2 into h by g, this formula is independent of the mass. This is independent of mass, whether it is a proton or an electron. Acceleration due to gravity does not depend on the mass, but due to electric force, the mass plays an important role in determining how fast it goes, etc. So when you do the calculation for just simple gravity, there is no mass involved, but here, like you can see, because electron and proton have different masses, the time taken are also different. So this is very, very important that we have ignored the acceleration due to gravity, because gravitational is a very weak force. Also, the heavier particle took more time for the same distance. This is in contrast, very, very important. This is in contrast, where in case of a free fall under gravity, the time of fall does not depend on the mass of the body. Does not depend on the mass of the body. Okay. Is that clear till this point? Yes, Srihari, we are doing as much as possible. Yep, yep. Hari Hara Priyan. Not sure, bacha. Let's see. Whatever happens till 8 o'clock. Okay. We'll see. I don't want to overload you also. 2-point charges, Q1, Q2. Magnitude this and this are placed at so distance apart. Find the field at point A, B, and C. Okay, let's see what happens in each of these cases. First, if you talk about point A, first, if you talk about this particular point A, this charge and this charge will give a repulsive field like this. It will give a field in this direction, radially outward. This negative charge will give an inward field like this. So the resultant field at basically point A will be field due to the positive charge plus the field due to the negative charge. Everybody till this point clear? Similarly, if you go to this particular point number B over here, this positive will give a field here radially outwards. This negative at this point will give an attractive field exactly opposite. So E negative will be here, E positive will be here. So the net electric field at point B will be electric field due to the positive minus electric field due to the negative, because they are both opposite in direction. I hope this point is also clear. Next, if you go to this particular point, this positive charge will give an electric field here. This negative charge will give an attractive electric field over here. This will be E negative. These two together will produce a resultant over here. So imagine if this particular angle is theta, even this will be theta, even this will be theta. So this E positive will have a component in this direction, which will be E positive cos theta. This will also have a component in this direction, which will be E negative cos theta. There will be also perpendicular components like this. There will be also perpendicular components like this. This will be E negative sine theta, and this will be also E negative sine theta. What will happen is these two components will end up cancelling each other, and what will happen is the resultant electric field at point C will be the sum of these horizontal components. So E positive cos theta plus excuse me, E negative cos theta. So you can take E positive plus E negative cos theta common over here. These are the three different scenarios, at least vector wise. In the first case, positive and this negative both gave the force in the same direction. In this point, positive gave force here, negative gave field here. Cancelled out, not completely, something will be remaining. We'll find out how much is the remainder. And in this case, this positive gave here, this negative gave here. So both are in these directions. So there will be cos components, there will be sine components. Sine components will cancel, cos components in the same direction will add to produce the resultant at point C. Is that clear? We didn't consider half. Where? Oh, sorry. I think I missed that number too. Sorry, guys. That 2 should be there over here. Sorry. That 2 into m into d, that 2 was there here. I think I missed writing that 2. Thank you for pointing it out. Okay. So now, in order to find each one of them, it's nothing but substitution. Electric field is nothing but K into Q. What is Q? 10 to the power 10 to the power minus 8 divided by distance. Distance is 0.05 square. And this value of K will be nothing but 9 into 10 to the power 9. That's it. Same thing for this also. Both of them magnitudes are same because this distance and this distance are same. Substituting these values, you can find EA. Substituting both these values, you will find EA. What about EB? So how much is E positive? How much is E negative? So this distance is 0.05. So it will be 9 into 10 to the power 9 into charge, which is 10 to the power minus 8, divided by distance, which is 0.05 square. How much is E negative? 9 into 10 to the power 9, charge is 10 to the power minus 8, magnitude only, distance. This is 0.5, 0.5, 0.05. So 3 times 0.05 whole square. That's it. Substitute these two, subtract them, you will get the answer for EB. Is that clear? Remember, this 3 times 0.05 is the distance of this point from the negative charge. Why did I not consider minus sign? Because I have already considered it over here. So you will not consider it 2 times. I have already written down negative because I know the directions are opposite. So why will you do it again? It's already taken. Yes. Is that clear? Perfect. Similarly, over here, what will this distance be? This is 0.1. So E positive or E negative magnitude wise will be the same. It will be 9 into 10 to the power 9. Charge is 10 to the power minus 8 divided by distance. Distance is 0.1 square. What is cos theta? Cos theta is adjacent by hypotenuse. So adjacent is 0.05. Hypotenuse is 0.1. Adjacent by hypotenuse. Substitute it, add them, you will get the value of EC. That's what they have exactly done at all these places, and they have found out all the answers. EA, EB, and EC, I think this is. Okay, that's what they have done. Is that clear? Did you understand how these things come? Calculation part, forget it. But for now, this much part, have you understood, guys? Give me a thumbs up. Give me a thumbs up, everyone. EA, EB, and EC. Is it absolutely clear? Shall we go ahead? Yes, come on. Cool. Let's go ahead. Just 1 second. Cool. Very good. Let's move. Let's move. Now that we have understood how to calculate the electric field due to multiple charges, what is electric field, the formula for it, let's talk about the next property, which is the electric field lines property. There are these things, imaginary things, which we call as the electric field lines, that is mentioned in 1.8 section. And they say that these concepts help us understand the behavior of other charges placed in the vicinity of a charge. What direction will be the force? How much large will be the force? Whether there will be force or no at all. So this concepts you can understand by this concept of electrical field lines. So they say that, okay, we have studied this, draw vectors pointing in the direction of the electric field line with their lengths proportional to the strength of the field. And at each point, since the magnitude of the field at each point decreases inversely as a square, the vector gets shorter as one goes away. So what they tell you is, basically, you go to any place and see how much the electric field is. Okay, it's very strong. You draw a longer line. Then you go to the next point and then see what is the electric field there. If it is less, show a shorter arrow mark. You go to the next point. See what is the electric field there? Because you have gone far away, the field will be shorter. So show a smaller line. So if you join all these lines, what you get is basically an electric field line. It shows what the force will be, how strong will it be, which direction will it be, etc. Inward, outward, everything. Okay, so that is what basically electric field lines are. So they have mentioned it over here. Connecting the arrows pointing in one direction, and the resulting figure represents a electrical field line. We thus get many field lines. We thus get many field lines all pointing outwards from the point charge. Have we lost the information of the electric field now? No, because when you go very close to the charge, you will see the field is very strong. You will see the spacing between them is less as compared to the spacing when you are far away. So it is more dense over here versus it is not so dense over here. So the density of the field lines tells you the strength of the field. So that is what they have mentioned. The density of the field lines is more. The density of the field lines is more near the charge, and the lines are closer. Away from the charge, you will see the field lines get weaker and the density is less. So resulting in well separated lines. So how close or how far the field lines are tells you the strength of the field. Same thing over here. If the field lines go like this, the field over here is definitely weak. Here, I will say it is strong because I can see that the field lines are closer, they are denser in that particular region. Clear till this point, everyone? Now, this paragraph is often misleading for many students. Sir, what is this paragraph, sir? Because they introduced solid angle and all that over here. See, I'll tell you what. In this particular diagram, there is a charge here. Electric field lines are coming in all the different directions. Now, whether you are close or whether you are far, if you take this particular red shaded area, which looks like the base of the cone, with this as the apex or the vertex, you can see this is like a cone, the number of field lines are the same whether it is this one or this one. Do you guys agree? Just check that out. The number of field lines are the same. You take this base of the cone or this base of the cone, it is one and the same thing. So one might think, sir, since the number of field lines passing through this and this in this particular region is the same, so will the field be the same? The answer is no. Why? Because even if the number of lines are same, now they are far away from each other, they are distributed over a larger area. So because they are distributed over a larger area, their density has become less. So the field intensity also becomes less. So when we talk about the density of the field lines, which also measures how strong that field is, we are basically talking about the number of field lines per unit area. That is what it means over here. So if one wishes to estimate the density of field lines, one has to consider the number of lines. If you want to measure the density of field lines, one has to consider the number of field lines per unit cross-sectional area, per unit cross-sectional area perpendicular to the lines. So if you take a unit area, how many lines are going per unit area tells me the strength of the field. You take per unit area. Here, same lines in a small area. Here, the same lines but in a larger area. So number of lines per unit area is less, hence the field is going to be weaker. Is that clear, everyone? Till this point? Yep. Very good. Very good. Awesome. Now, in the next paragraph, don't worry, guys. We'll be having a break in a bit. In fact, yes, we'll be having a break. Don't worry. Yeah, just give me some time. Maybe just after this particular thing, we'll be having a break. Okay. Yeah. In the next particular paragraph, what they mention is basically, see, there is this concept called as solid angle. If you have forgotten, let me just remind you of this. If you have an arc If this is the theta, this is the radius, the length of the arc is basically r into theta. This is basically called as your plane angle. This is basically called as your plane angle. Then if you have an area, not an arc, an area, then at a point what it subtends is not an angle in 2D, but some weird looking figure, angle in 3 dimension. This is also called as solid angle. This is called as solid angle. If this solid angle is psi, the distance of this area from this point is r, then this area which you are seeing right over here, this area which you are seeing right over here, this area which you are seeing right over here is r square times this solid angle. R square times this solid angle. Plane angle is measured in radian. Plane angle is measured in radian, right? Solid angle is measured in steradian. Is measured in steradian. This is what you should know. Till this point, is it clear? Till this point, is it clear? Difference between plane angle and solid angle. Just like length is r into theta, here area of any shape is r square times the solid angle. It's an angle in 3D. It's not in plane. Imagine that in 3 dimension, which is subtended by that area at this particular point. Now, what happens is, if you take any shape which has basically the same solid angle, now whether you take this part over here versus you take this part over here, they both have the same solid angle. They have the same solid angle. Same solid angle, right? They have the same solid angle. And what is same through both of them? What is same through both of them is the number of lines which are cutting through. Is the number of lines, n number of electric field lines which are cutting through it. But still, what is different is the electric field strength here as well as here. Because here it is close, here it is far away. The electric field strength is different. So why is that electric field strength different apart from visually, mathematically? How do I prove it? See, if the number of lines is n, the number of lines per unit area, the number of lines per unit area, what is that area which is there either here or here? What is that area? What is that particular area? That area is nothing but, remember I just gave you the definition, solid angle's area is r square into psi. So r square into psi, so it will be nothing but r square into psi. The number of lines is still the same. This gives me the electric field value. Since n is same, psi is same, what is different is r, how far I am from this point. This guy's r is less, this guy's r is more. So you can clearly see electric field is inversely proportional to r square, exactly what we know from before also. Electric field value is kq by r square. The same thing is also proven using this solid angle concept. This is exactly what has been written in this entire paragraph in a much more complicated manner, which I have given it to you in a much more easier manner. As the same conclusion, you will see that the electric field strength has a 1 by r square dependence. 1 by r square dependence. Exactly what I have shown over here. Is that clear? Okay, what this entire paragraph says? Very good. Awesome. Now, the next important thing about electric field lines properties. So, see, we get lost sometimes where we were. So, electric field lines, first of all, the definition. You start from a point, show the field arrow mark, go to the next point, see the field where it is. Keep joining those lines, you get electric field lines. If they are closer, it is strong. If it is far away, it is weak. That is the first thing. Electric field lines also tells me the direction in which the force will act. Now, you will see that the next important property is that they will never ever interact, sorry, never ever intersect with each other, although it is not mentioned over here, but it is always going to be true, right? I have not mentioned it over here, but that is always going to be true. This is not possible. You will never ever see this is ever going to happen. So this is never possible. This is never ever possible, because then it will have two different directions of forces, which is not possible. It is either this or that. You can't have two random directions at the same time. Okay. Now, they have given some configurations and they have shown how the electric field lines act. Look at all these things, very, very straightforward. If you just have a positive charge, what will happen? All the electric field lines will tend to go outward, radially outward, exactly what you would expect. If it is a pure negative charge, you will see all the electric field lines will come radially inwards. It will come radially inwards, isn't it? Similarly, if you have two positive charges side by side, or one positive, one negative charge side by side, then what will happen? Both these positive charges will generate electric fields, but since the field lines can't intersect each other, they will come close and they'll go away. They'll come close and they'll go away. And they feel like as if they are running away from each other because they are repelling charges. Here, one is positive, one is negative, one is a giver, one is a taker. So whatever field lines comes out of positive enters into the negative. Whatever field lines comes out of positive eventually goes into the negative, because this gives and this takes. So these are the some of the interesting things which you can note down over here. Field lines always start from positive. Field lines always, they will start from positive charges, and they will always end at negative charges. If there is a single charge, if there is only 1 point charge, okay, if there is a single charge, then they may start or end at infinity, like the one here. They are ending at infinity. Here they have started from infinity to end over here, which kind of makes sense. When there is no charge, electric field lines can be taken to be continuous curves without any breaks. In a charge-free region, basically, imagine this is the region when there is no charge. You can see electric field lines are continuous. There is no breaks, like suddenly there is nothing in between, or suddenly there is electric field, suddenly there is no electric field, suddenly there is electric field. This won't happen. You will see they are continuous, which kind of makes sense. So electric field lines are continuous curves without any breaks. Two field lines cannot intersect each other. That is something which I already mentioned. They can never cross each other, because if they did, then they will have two different directions, which does not make sense. Electric field lines do not form any closed loops. Again, meaning, imagine a field line starting from here and ending onto itself. Starting and ending onto itself. This is a closed loop. This is not possible. This is not possible again. Okay. So electrostatic field lines do not form closed loops. They will start somewhere and they will end somewhere, but they will not end on itself. That is what this last point means. Okay. These are the main things. So we have come to the next concept of electric flux, I believe. I think we can just probably do this before taking a break. What say, guys? Let's do electric flux concept before taking a break. Ready? Ready for it? Electric flux? Or shall we do it in part 2? What say? Electric flux, we'll do this, and whatever is there after this, it's quite a lot actually. Electric dipole, and yes, Gauss law applications, field due to dipole, forces on dipole, etc. Shall we do it in the next lecture? Part 2, we'll do it separately. What say? Yeah. So that I can study till here. Monday only I will take it up. But then I want full attendance in the next class again. Yeah, let's do that. Okay, let's do electric flux today. We'll finish this part in part 1, and then we'll take up part 2 separately. So See guys, what is the meaning of flux? They have mentioned over here. Okay. Sure. They mention that consider the flow of a liquid with velocity v through a small flat surface. The rate of flow of a liquid is given by volume crossing the area per unit time and represents the flux of the flowing liquid across the plane. So, the rate of flow of the liquid is given to me. Area per unit time, okay. And over here, they are talking about something called as the volume flux. Therefore, the flux is going out of the surface. Okay. So then they compare it with electric flux. See, in fluid mechanics later on, you will study something called as streamline flow, etc. And if you are given a pipe like so, you can find the flux of the flow of that particular liquid. It basically means the flow rate, how much volume of the liquid is going per unit time through that particular, pipe. That is the flow of the liquid, which is also called as the flux of the flow of the liquid. That is for fluids. Similarly, when you have electric field lines, which are going like this, looks like liquid going through a pipe. So we also can define something called as the flux of the electric field. The only difference being there is nothing actually moving. There is nothing actually flowing physically, unlike the liquid flow. In case of the liquid particles are actually moving in the pipe, but in case of electric field, you do not see some particles going. It is just a hypothetical concept, because electric field only was purely hypothetical. It was imaginary, which helps us understand physics better. So the same thing can be said definition wise, but don't expect anything to actually see. So flux of electric field means the flow of the field lines, the flow of the field lines. How much flow is there? If there are more field lines, then the flux is higher. So basically, always remember electric flux is directly proportional to the number of field lines through an area. That's what it would be. If there are more lines passing through an area, it has more flux. Okay. For that, they have given different examples. Starting off with this. Imagine this rectangular sheet. Imagine these field lines intersecting that rectangular sheet. If you look at it from the side way or from the top view, basically, if you look at it from the top view, you will see the field lines are moving perpendicular to that sheet. If you look at it from the top, the field lines are basically going through that sheet perpendicular to it. Now, what they have done in the next scenario is that they have taken this sheet and turned it slightly here. You can see it has been turned slightly here. So now the field lines will make an angle. So if you look at it from the top, because the sheet was turned, you can see that now there are different number of lines cutting through that sheet. Earlier, when the sheet was like this, all these field lines were intersecting that sheet. But the moment you turned it, do you see some of the field lines are missing that sheet? They are no longer cutting through that sheet. That means the flux has changed. That means the flux has reduced. Everyone? So don't you see that the flux completely depends on how many lines cut through it, and that further depends on how you are placing that sheet. If you change the orientation of the sheet, you will automatically see that the number of lines will reduce or increase. Also, imagine somebody turns the sheet enough and makes the sheet like this, then all the fields will go in front or behind of the sheet. Nothing will cut through the sheet. Nothing will cut through the sheet. Then the flux will become completely zero. Then the flux will become completely zero. That is what they have mentioned here. If theta was 90, imagine here theta is 0. Slowly you change the theta value and make it 90. So this sheet finally becomes parallel to the field lines. You will see all the field lines will go front or behind it, nothing cutting through the sheet. So the flux will then become zero. So therefore, they say that over here that the orientation of the area decides the magnitude of the flux, okay, in different scenarios. How you place that particular area helps you decide how much flux is passing through it. Why this concept of flux is introduced, you will understand it in Gauss law. For now, we are just introducing this concept of electric flux for now. Now, they also mention now, next point, we define whatever this surface that you see over here, this surface that you see over here, we define that surface as a vector quantity. Yep. And the vector quantity of area, the vector quantity of area is always perpendicular to the area, is always perpendicular to the area. You can see this is that area vector. It is in this case here. Okay. It is always perpendicular to that area vector. Here in this case, it was here. This area has been defined as a vector quantity. It is always defined as a vector which is perpendicular to that particular surface. So if you hold a normal, if you draw a normal, to that particular surface, what you get is the area vector. So how do we define that particular flux? Simply put, the electric field into basically the area into the cosine of the angle between the area vector and the electric field vector is the electric flux. The symbol of electric flux is phi. Because electric field is a vector, area is a vector, and you see cos between them, that's why you often write it as electric field dot area vector. Electric field dot area vector. That is what they have also mentioned over here. Some books use the symbol A, some books will use the symbol S for the surface area. This is the definition of electric flux formula wise. And the unit of electric flux will be Newton per Coulomb into meter square, because electric field was Newton per Coulomb. This was meter square. So that's why Newton per Coulomb into meter square. As simple as that. Now, if till here everything is clear, one might have a question, sir, if I have a surface, should I take area vector here or here? Because even this is perpendicular, this is perpendicular. The answer is both are correct. There is nothing wrong in either of them. Both are correct. So you can take the normal vector here or you can take the perpendicular vector here. Both will be fine. This is okay as long as the area is basically open. The area is basically an open area. This is also allowed. This is also allowed. What is the meaning of an open area? Imagine this thing. This is a surface. It could be curved, twisted, bent, flat. So this is an open area. But somebody decides to stitch it. Even this opening, it becomes completely closed. It becomes completely closed. Then that is called as a closed area. Then only the vector or the area vector which points outward is correct and it is considered as positive. The vector which goes inside is then negative. The vector which goes inside will be then negative. Keep that in mind. So the sign convention is there only for closed diagrams. Is only there for closed diagrams. For open diagrams, you can choose this or this. Both will be fine. But for closed diagrams, the one which goes out is positive. The one which goes in will be negative. Keep that in mind. Is that clear? Absolutely. Perfect. So we'll do electric dipole, etc. later on. Okay. For now, till this point, ah, my bad. Okay. So we'll do this point later on. Okay. So I'm not able to take many classes also because of this throat issue. That's why I had to shift my class from Friday to Saturday also, because I thought it is going to get better. It's not getting any better. So as soon as I start feeling much better, I think I'll increase the number of frequency of my classes as well. Okay. For now, I think this much is enough. Part one. We'll do part two in the next class. All right. Take care, guys. Bye bye. Have a great time. Hasta la vista.